All right, BC number 3, multiple choice packet. This is the third and final BC packet. So these are helpful to review ideas that you are even on for your response. So this one is all about integration by parts, partial fractions, improper integrals, and L'Hopital's rule. So let's review integration by parts. I think we saw at least one problem in the last practice test that multiple choice that involved integration by parts. A lot of times they kind of give you, I don't know, it seems like a lot of times they kind of give you kind of creative problems with that involve these. Okay, so integration by parts is a reverse product rule. So we waited to teach you guys how to do this till this year in Calc BC. It's not covered on the AB exam. So it generally starts with something that involves a product. And one part of it's going to involve two things multiplying each other. Now, sometimes you have two things dividing, and then so you got to think of the division as multiplication by like a negative power. Or the idea, I mean, this is sort of something that I think we'll memorize. I don't think I'm going to rederive this right now. But we get uv and minus the integral of vu prime. Now, I don't know if I'd really memorize this because I feel like there's a pattern that I use. But one of the first things is to decide which part is the u and which part is the v prime. So we'll start with the u. And Lipet, Lipet, gives you the precedence of what should be chosen as your u. Now you gotta remember what these stand for. L is for logs, which would include natural logs. I is for inverse trig, kind of interesting. P is for polynomials, which are pretty common. Even if you just get a number, you could treat that as a polynomial. E is for exponential, so that'd be base E or any base. And T is for trig, like regular trig. There's a shortcut that we can use for polyexpo or polytrig. And it's generally worth it, even if it's because we might have to use this process multiple times. And polyexpo, polytrig, that often comes up when poly is your u. And so there's a nice shortcut. So we'll do some of those. Improper integrals. I think we've brought these up recently. You have to break up at vertical asymptotes. By the way, we're going to probably use all of this space over here for partial fractions. I have to break up the vertical asymptotes, which we call, the technical name of them are infinite discontinuities. So if you have vertical asymptote in the middle of what you're integrating, technically it blows up and you kind of have to deal with it as a limit because that value is not actually defined. So you can't really just like integrate and pretend like it's part of the function. So you got to break it up. And we have to change. So what happens is we change interior discontinuities. So that means in the middle of the limits, interior discontinuities into endpoint discontinuities. So sometimes we get a vertical asymptote at the edge, and we have a way of dealing with that. We change it to a limit, but when we have ones that are in the middle, we break it up, and then they become like endpoint discontinuities. We have to use limits as we approach vertical asymptotes. At endpoint discontinuities. So we'll do some problems like that. Also, partial fractions, which is really just like an algebra technique, but it seems like in your math education we've probably avoided that. But it's a technique that can be taught at lower levels of algebra, but it just becomes necessary in Calc BC where it didn't seem to come up before. And so we'll just talk about that technique first. So let's see. If you have a fraction, we can't just, we can distribute the denominator to the separate terms in the numerator, but other than that, we can't really break up the denominator. But so this is a way to do that. So if you can factor the denominator, what we're going to do is we're going to rewrite it as two separate terms, partial fractions that are part of the original fraction, that have each factor of the original denominator as separate denominators. The method is that we multiply through both sides by the least common denominator, which is original denominator. It gets rid of all the fractions, all the denominators, and then we want to figure out what the a and the b values are. The easiest way to do that is to plug values of x in here. That'll make one of them go away at a time. It doesn't matter which one you do first, usually. So if you plug a 0 in, that term goes away, and we get 2 equals a. Then we could plug a -1 in to make the a go away, and we get -1 equals -b, so b equals 1. And so then these partial fractions end up being 2 over x plus 1 over x plus 1. And then you're able to integrate that. And so the reason this comes up is if we're trying to integrate this, use substitution doesn't work, other methods don't work. We got to break them up. Once we break them up, it's not a problem to integrate them. And they generally create a bunch of natural log antiderivatives that a lot of times will combine back together. So that's partial fractions. Now, there are some special cases. There's one where you have repeated factors. So I'll give you an example of that. 3x plus 2 over x cubed plus x squared. If we factored it, it'd be 3x plus 2 over x squared x plus 1. And this is a repeated factor. And so when you go to write it, you're not going to write a over x and b over x. You're going to write a over x squared. And then you're going to write b over x. And then you're going to write c over x plus 1. So the repeated factor, one of the terms is going to have it repeated, and one of the terms is going to have it by itself once. The technique after that is similar. We multiply through by the least common denominator, and we get 3x plus 2 equals a x plus 1 plus b times x plus 1 plus c times x squared. Now we could say, well, let's plug a 0 in for all the x's. And then that would make both of these terms go away, and you get your a value. A equals 2. Now, if we didn't do that, let's keep going. If we do a -1 in all of the x values, then we get -1 equals, that goes to 0, that goes to 0. -1 squared is 1, so that's your c value. Now we got to find b, but there's no way to find b by just getting, if we plug a -1 to get rid of the a, it gets rid of the b too. If we plug in x equals 0, it gets rid of c, but it also gets rid of the b. So we actually need to find the a and the c values first, and then plug them in to this. And then, so we can plug any value of x, and this is a technique we could often use in general. It's just easier if you make one term go away completely. that's the easiest way to get these results. The only problem is it's not going to work now for B. So we're going to plug the A and the C values in, and then any value for X you want. We don't need to make these terms go away anymore because we actually have the A and the C values. The reason we make them go away is because we don't know what they are yet, or we don't want to use those values. It's simpler. So I don't know. I plug in X equals 1. Seems like a good value. So I'm going to plug in X equals 1 and A value is 2. And the C value is -1. Okay, so then we get 5 equals 4 plus 2b minus 1. So then 2b equals 2 and b equals 1. So sometimes you're going to have to find certain coefficients first and then use them to find another coefficient. So these are our final values. So the final answer is 2 over x squared plus 1 over x minus 1 over x plus 1. Now, when you integrate these, you're going to get some natural logs, but then that one's going to be a power rule. So there you go. That's the notes part of this packet. So now we're going to try some problems. So why don't you guys try 1 and 2. Pause the video. We just did a bunch of notes and stuff. Pause the video and see if you can do those. Okay? And then unpause it, and we'll check your answers and see how you did. So number 1 says, in decomposing, that means to break apart, by the method of partial fractions, one of the fractions obtained is one of these. So it seems like we're probably just going to need to break them up and get them both, and then one of them hopefully will be in that list. So this one's already factored. So we're going to write equals a over x minus 7 plus b over x plus 4. Now, it really doesn't matter which one you put the a or the b over. You'll get the right answers. You'll get the same number that goes with x minus 7, no matter what letter you put there. We're going to multiply through by the least common denominator to get rid of all the fractions. And then we're going to try and, like, we could plug a 7 in to all the x's. This can be 35. This can be 33 equals 11a, and that term goes away. So a equals 3. And I mean, you could even stop right now and say, oh, there it is. But let's act like maybe that one didn't turn out to be one of the ones on the list. So let's see, what would we do to find the b value? So that'd be negative 22 equals negative 11b. So b equals 2. So the answer is going to be 3 over x minus 7 plus 2 over x plus 4. And so 3 over x minus 7 is only 1. All right, number 2. One of the things about improper integrals is sometimes you have to understand that they're coming without. Now, if there's infinities and limits, then that's obvious. You're going to have to use limits. But you want to check t can equal -1 and t cannot equal 4 because there's vertical asymptotes. Now, if either of these values if these values don't happen where we're integrating, then we can ignore it. But this one's at the edge. So technically, to rewrite this, we don't have to break it up because we don't have any interior discontinuities. We might need to use partial fractions on this problem, but if you look at the answers, they're not going to make you actually finish the integration. They just want you to rewrite it in its most proper form. Now, positive 1 is fine, but then up here, a lot of times what we do is we put like a b or something, and then we say the limit as b approaches 4. Now, it's a one-side limit. We're approaching it from the left side, so a little superscript negative. So we're looking for one that kind of looks like that. I mean, they're using x's. That's fine. And so this one has it, but it doesn't have it in the right spot. It should be there, and that should be that. So I think this is it, right? So they're just... Now, for your response, like if this were multiple choice and we had to keep going, I might not rewrite it as the limit. I might put a little 4 superscript negative there to remind myself and be lazy. On free response, you better rewrite it like this and actually show the technical limits throughout the work. Okay, let's go to the next page. Why don't you guys try 3 and 4? So pause the video and try 3 and 4. So 3 looks like we got to integrate it, find the antiderivative. It's an indefinite integral. And so we need to, I think we're going to have to do partial fractions, right? So can we factor this? Got to be able to factor correctly. It's got to be a 1 and a 1, both positive. Does that give you the 3x in the middle? It does. So we're going to rewrite it as a over 2x plus 1 plus b over x plus 1. And so we're going to have to find those coefficients. So we're going to multiply through by the least common denominator. The top is a 1. Equals a, x plus 1, plus b, 2x plus 1. And I'm going to plug a negative 1/2 in to make the b's go away. I get 1 equals a times 1/2. So a equals 2. Then I'm going to plug a negative 1 in so that the a's go away, and I get 1 equals negative b. So b equals negative 1. And so then I'm going to integrate it. I'm going to jump down here and say, okay, well, I'm integrating. Now, I usually break these up. I say, okay, and I put these numbers just out in front as a coefficient. 2 over 2 integrating dx over 2x plus 1 minus 1 integrating dx over x plus 1. And so we're going to get 2 natural log the absolute value of 2x plus 1, but the 2 is going to pop out because of the chain rule, so we need a 1/2 to counter it, minus natural log the absolute value of x plus 1. You need the absolute values, plus c. Those 2's cancel. Now all these answers have these logs combined, so we got to use log rules. So if it's subtraction, it becomes division. We could just put them inside one big absolute value. So is that answer on here? Let's see. There it is. It's D, which I think I had the wrong answers listed on my solution sheet, but if you're watching the video, you got it right. All these other answers are based off of really common mistakes. Like this one right here has a squared inside because that's for the people who forgot the 1/2 and they brought it inside before they combine them, which is what you would need to do. This one is for the people who got the 2, forgot the 1/2, and then I guess decided that they could just leave it out in front before they combine these natural logs, which you can do. So that's like double mistake. This one, it's upside down. So something messed up. Either they got the wrong coefficients or something. This one, they multiply the insides because maybe they got a plus. Maybe they messed up the sign here. So it's kind of all these wrong answers kind of represent some really common mistakes. Number 4, if you're trying to integrate this, you might be like, oh, I'm going to do u substitution. No. So we can't integrate this with any techniques that I taught you guys in Calc AB, but this is something times something else. So we might try integration by parts, LIPIT, which I always like to write this. It's a nice little checklist, and I kind of circle which ones I have. I even write down here, I got poly, expo. Now, poly expo is also one of the ones that you could use the shortcut on. So, I could show you 2 different ways of doing it. So the shortcut, I think it's worth it even on this problem, which isn't terrible. What you do is you take these and now also realize this is a definite integral. So we're going to plug those in later after we get the antiderivative correctly. You have poly, which is, this is your u and this is your v prime, right? The first one in the list is your u, and that's the one you're going to take the derivative of. So we take the derivative of it repeatedly till we get a 0. And the other one we have to integrate, right? So we do the antiderivative and we keep doing the antiderivative. And then we're going to multiply these down at a diagonal. Okay, now once you get to the 0, you're done. The other thing you got to watch out for is the first one's going to be positive and the next one's negative, and they keep alternating sign. The reason is, I'll show you the work in a second doing it the regular way. So what we get is we get x e to the x e to the x, minus e to the x, okay? And then it's a definite integral, 0 to 2. So it's going to be 2e to the 2 minus e to the 2 minus 0 times e to the 0 minus e to the 0. That goes away. That's a 1. So we get 2e squared minus e squared plus 1. These are like terms, so that's 1e squared plus 1. Now the long way of doing it is to be like, okay, my u is the poly, and my b prime is the expo. And we usually put the dx with the derivative, because that's a derivative. And then you say, okay, let's find u prime, which is 1, dx. And then we integrate this to find v, which is e to the x. And then the pattern is, it's uv, which I feel like I can remember, that it's always going to be uv, minus, got to remember the minus, the two new things multiplying each other. So that's e to the x dx. And this is where that alternating sign is coming from up in the shortcut, is that we subtract. So then if we have to do it again, we get another subtraction, but it becomes addition. Now, what should happen is that this should be either getting closer to something you can integrate, or it is something you integrate. So you can actually finish it, right? So we get the same thing, keep going. But the shortcut's kind of worth it. I mean, even here, I feel like it's quicker. But if you had like an x squared, you're going to have to do this process multiple times doing it the long way. And this will just crank it out real quick. All right. Let's see. Let's go to the next page and let's try the first two problems, 7 and 8. So pause the video and try 7 and 8 if you haven't yet. So this one is a limit problem. So this looks like L'Hopital's rule, which I think we brought up recently in another packet. If you plug 2 in, you get 2 to the first, right? Minus 2 is 0. And you get 2 squared minus 4 is 4 minus 4 is 0. And it's multiple choice, so we're going to be lazy about it and just say, all right, this equals the limit as x approaches 2 of the derivative. Now, what's the derivative? The derivative of these guys are 0, so it's really this and this. What's the derivative of an exponential? So we're used to e to the x's. Those are pretty easy. But any exponential is its own derivative, but then it's followed by the natural log of the base. Now it works for e also, because the natural log of e is 1 and goes away, and we just usually don't write it. But there's a chain rule issue in here too, that you got to multiply by the derivative of what's inside. So you get that whole thing. The bottom is going to be 2 to the x, natural log of 2. Now these clean up quite a bit. The natural log of 2's go away. And rules of exponents. Let's see, can we use rules of exponents here? We're going to get... oh, no, we're going to plug 2 in. Let's just go and plug 2 in. I don't think I want to use rules of exponents. I could. I mean, sure. Let's use rules of exponents first. We won't take the limit yet. So it's going to be a 1/2 2 to the x over 2 minus x, right? Rules of exponents. So that's going to be 1/2 times 2. If you plug 2 in here, it's going to be 1 minus 2. That's a negative 1. So it's going to be 1 over 2 times 1 over 2 is 1/4. So a little L'Hopital's rule for you. Number 8, which of the following improper integrals converges? And that means it gives you an answer, because improper integrals can blow up to infinity because they involve either integrating to infinity, like an infinite area, left to right, limits, or it might involve integrating a function that blows up to infinity right where you're integrating. So sometimes those diverge, sometimes those converge. So I think our best bet is to actually just do these problems. So this is going to be, the answer of this is going to be e to the negative x with an extra negative, all right, 0 to infinity. 1 over e to the x, negative 1 over, I think that's a little easier. So it's going to be negative 1 over e to the infinity minus negative 1 over e to the 0. That's going to go to 0. This is going to be 1. So that one converges. If it gives you a nice answer, that converges. So that one converges. This one is the same as x to the negative 2. So that, now the issue here is that x can't equal 0. So technically, we should be integrating the 0 from the right-hand side. We should be approaching the 0 from the right-hand side because it's between 0 and 1. So we're integrating from the right side of 0. So I'm going to be lazy and just put the little plus here. If it were for response, you want to rewrite it as the limit as b approaches 0 plus and put a little b there. So the antiderivative is negative 1 divided by the new exponent, 0 plus to 1. And so that's going to be negative 1 over x, 0 plus to 1. And so it's going to be negative 1 over 1 minus negative 1 over 0 plus. Now that's negative 1 plus. Now 0 plus means we're dividing by a tiny number, which means this is going to blow up. Now, does it blow up to positive infinity or negative infinity? Well, if we're approaching 0 from the right, that means it's positive. We're dividing 1 by a very tiny positive number, which means it's going to blow up. Now, this is technically not the answer. The answer is diverges. Infinity is not really supposed to be an answer, so that one diverges. This one is the same thing as, this one has an endpoint to infinite discontinuity. So the graph has a vertical asymptote and goes to infinity as you approach 0. And technically, you can't plug 0 into it because it doesn't exist there. So that's why we're going to approach it from the right side. So this is the same thing as x to the negative 1/2. And the antiderivative is x to the 1/2 divided by the new exponent multiplied by the reciprocal, 0 plus to 1. So this is going to be 2 square root of 1 minus 2 square root of 0 plus. And that's going to be 2 minus. Now, the square root of something tiny is going to something tiny. So this converges. So 1 and 3 converge. So a little improper integral practice for you. Let's keep going to the next page, and I'll have you guys try a couple more of these. Why don't you guys try 11 and 12? So pause the video, try 11 and 12. So 11 looks potentially like a L'Hopital's rule. This is going to go to 0, right? So, but then this is going to be infinity, and that's going to be infinity. That's going to go to 0. Now, these are the dominant terms, so we don't have to really use L'Hopital's rule here because I think it's pretty clear that it's going to be the ratio of those coefficients of matching terms. So that'd be the easiest way. L'Hopital's rule is not always like a magical shortcut. It often can be more work than just, especially with infinity. In behavior, I think we can think of a little differently. Now, number 12 is the integral of e to the negative absolute value of x. It has infinities in its limits, so this is an improper integral. There's no vertical asymptotes here, right? Anywhere. It might be good to kind of give yourself an idea of what this graph looks like. As you go to infinity, this is the same thing as this, right? So as you go to infinity, it goes to 0, and it's going from the top on both sides. It's going to y equals 0. So it has a horizontal asymptote on both sides. When you plug 0 in, it's 1. And anything smaller is going to be smaller than that. So because any exponent bigger than 0 is going to be e to a bigger exponent, which is going to make the denominator bigger, which is going to make the overall thing smaller. So this is what we're trying to find, and we're trying to find the area underneath the whole thing. Now, one thing we could take advantage of, now that we understand that this graph is symmetric, is we could just integrate half of it and double the answer. And that would be convenient. I guess I could show you either way. And since if we're doing 0 to infinity, then we know that we're dealing with positive x's, so we can just drop the absolute values. And then we don't have to worry about the absolute values. So this is going to be e to the negative x negative 0 to infinity. So that's a negative 1 over e to the x. 0 to infinity. So that's a negative 1 over e to the infinity minus negative 1 over e to the 0. That goes to 0. That goes to positive 1. The answer is 2 because we got to double it. So that's one way. The other way is to not try and do that at all and think, well, I got it. In general, back in Calc AB, we say, well, how do we get rid of absolute values? In general, since Algebra 1, how do you get rid of absolute values is you break them up into their different cases. You break it up where there's positive inside or the negative inside. So when does that happen? That happens at x equals 0. So we'd say, okay, well, let's do negative infinity to 0 of e, and I'll finish that in a second. And then let's do 0 to positive infinity of e to the, now if x is negative, the absolute value is going to change its sign to a positive. So essentially, when x is negative, it's going to give you negative x, which then becomes a positive x there. And when x is positive, then we just drop the absolute values and the negative on the outside is still there. And so then we're going to add these together. So this is the way you would do it, kind of using techniques from Calc AB. And then, but you then have to integrate this, right? And then you have to integrate this. And then you have to do, all right, e to the 0 minus e to the negative infinity, which is 1 minus 1 over e to the infinity, which is 0. And then this is negative 1 over e to the infinity minus negative 1 over e to the 0. So that's 0. And that's 1. And you have a 1 plus 1, which is 2. So same answer. Let's see. Should we try 13 as the last one, and you guys can finish the rest on your own? Try 13. Pause the video. See if you can make any sense of it. So let's see. Let f be the function that is everywhere differentiable. The table below provides information about f of x and its first, second, third derivatives for different values of x. So we got a bunch of derivatives for various values. Which of the following best approximates f 2.2? Now look at those answers. What do those answers make you think of? Those look like series, right? So I think we're trying to do like a Taylor polynomial, right? So if we're trying to approximate 2.2, one question to ask yourself is, series converge, generally they have an interval of convergence around the center. So if you know you're going to calculate a certain value, then it might be better to use the closest value that we have information on as the center. So it might be best to do, so Taylor polynomial, and we're going to evaluate it at x equals 2.2, but let's choose the best center. Let's do the center at x equals 2. The other ones can maybe do a good job, but I think this is the one that we're going to want to use. Now, the Taylor polynomial should have f to the 0th power at the center, x minus the center to the 0th power over 0 factorial plus f prime at 2, x minus 2 to the first power over 1 factorial plus f second derivative 2, x minus 2 to the second power over 2 factorial, and so forth. So we're looking for the ones that have these values with the correct, let's see, so 7.2, I think it's got to be one of these, 7.2, and then 3.5. And then when we plug 2.2 in and it's centered at 2, then we should get 0.2s, 0.2, 0.2, 0.2. So this one's out. Oh, no, that one's in. Sorry. These ones are out. Because these would be centered at 0, but then the derivatives don't make sense. So these are just, not only are they like not the best, they look like they're centered at 0, but then they have the wrong derivatives. 1.75 over 2 factorial, 0.85 over 3 factorial. So this looks like the best one. These ones look like they're centered at 0, but then they have the wrong derivatives. This one looks like it's centered at 0 and it has the... Does it have the correct derivatives? 2.2. I don't know if these ones... I mean, this one looks close to what it should be if it were centered at 0. But I feel like there's a problem with this. This should be 2 times 2.2 to the first power of 1 factorial. So that one's wrong. It's not great center. This one looks like they're trying to center it based off the values in the parentheses, center it at x equals 2, but then they're using the wrong derivative values. So they're using the derivative values centered at 0. So that's it. Try the rest. Check your answers, fix them, and hopefully this will help you on your practice tests.